We'll not the second part of it.
On the second, you show me the first part.
So solubility, equilibria. So to get back in the mindset, big K, right? We said products over reactants, but only what states of matter?
Solid and liquid.
Okay,
Liquid and gas.
we do not have solids and liquids.
It's aqueous and
Gas.
gas.
Aqueous and gas are in that big K. Okay. Now, here's the problem. Solubility, solids, we will always have a solid on that left-hand side. Because it's we don't mess with solids. So that means you're only gonna have those products involved in the process.
Those products like over one.
It'd be over one. Yes, very good, because it's a quote unquote pure substance in this process here.
It would be
So-
like K would equal the products over one.
KEQ.
KEQ.
Yeah. Now, yes, KEQ, but we're dealing with solubility, so we change to SP. That's the only difference. All right. So we're going to go through these two examples. That's why I didn't do those when we wrote it down, because we're going to write it down here in just a second. Okay. So here we go on this. Oh, the other part here is you get a chart. This gives you the KSP values. These things are all solids, and that is the K value associated with these particular solids. I'm going to have you reference this chart, so if somebody could just flip back and forth and yell out some numbers, that would be great.
Go back, let me take a picture of this so I can yell out the numbers. All right, we're solid.
Good. Solid. I see what you did there. I like that, Corbin. All right, so here we go. Another thing that I did not like when I made these notes is I didn't like the equation. So I'm going to quickly give you the equation here of copper to carbonate breaking down into its different portions here. So we have copper carbonate, which is a solid, and it's equilibria. So remember, we draw these two arrows, and we break this down to copper with a 2+ charge, AQ, plus carbonate with a 2- charge, AQ. And that's something, like I said, I wish I would have put that up there, but we have it now. Now, writing the KSP, if I said, hey, write the KSP, you would put products over reactants, but you guys have already told me solids are going to be listed there. It's going to be over one. What's that?
The product.
Exactly. So in this case, we would just put Cu 2+, raise it to the coefficient of 1, which we're not going to put, times CO3 2-, also raised to that coefficient of 1. Poof, we've done that. Again, that would be divided by 1 because that's a solid, but we're not going to put that, okay? The next thing is this, and this is where I'm going to need you guys to help me out.
Okay.
For copper to carbonate, what is the value of CuCO3 in that chart?
0.5 times 10 to the negative 10.
Very good. So this comes from that chart. The number I just wrote down in green comes from that chart. That's in notes. You're going to get it. I'm not going to make you memorize it, obviously. But I'm going to replace that with that KSP. So we have 2.5 times 10 to the negative 10. Now, my next question is this. Do we know anything about copper or that carbonate, that CO3 2-? Is anything listed number-wise? So if we don't know it, we put what in math class? Variable. So we're going to put our x times our x, and then x times x becomes what? Very good. So let's consolidate this. Let's say 2.5 times 10 to the negative 10 equals x squared. Now, how do you get x by itself?
Square root.
You take that square root here, and so you're going to say square root, and so let me turn to my calculator. we get the square root of 2.5 times 10 to the negative 10th. And my x is 1.58 times 10 to the negative 5th. And the unit would be mole/L for liters. And that would be, quote unquote, the molar solubility. Okay. Now, as we go through this process here, we have some more things that we need to factor in. So any questions here? Okay. Does anybody need it? All right, I'm gonna move a little faster here and we'll go through this. The next part here is magnesium hydroxide. Cool, looks pretty similar, but I'm gonna throw up the equation real quick just like I did on the other slide. Magnesium hydroxide, it's a solid. Put that as a BOH2. There we go. Solubility, and then we have this Mg2+, which is AQ, plus OH minus, which is AQ. Now, we're missing something with the OH minus. Anybody know what that is?
Sorry.
How do we even that out? Yeah, we have to put a 2 coefficient, which is really important here because here we go with this. Our KSP, remember KSP is equal to Mg 2+ raised to what power? 1 times OH minus raised to what power? 2. You were right the first time. 2. That is really important. That's something people often just go right past. Now, I gave you the KSP, so you could find that in the chart if I did not give it to you, which is 5.6 times 10 to the negative 12. So in place here, I'm going to give you 5.6 times 10 to the negative 12. X, very good. And now here's something I'm going to have to teach you there. This is X. Now, we're going to have to put another X, but this 2 coefficient, not only does it make it the power, it makes it double. So we actually have to put a 2x squared, which is something, again, people often forget there. So now we're going to consolidate this. We're going to say 5.6 times 10 to the negative 12. I'm going to do this. I'm going to blank that other x out. 2x squared. What's 2 squared? 2 squared is 4. 4x also gets squared, so we get 4x squared. Now, 4x squared, x squared times another x. What's that do to our number of x's? There it is, I heard it. Cube. This technically is 4x cubed. Now, I want to get x cubed by itself. So what do I need to do with this 4? Divide it, yep. So we go divide by 4. Let me throw this in.
Shut up.
I don't know, be nice.
He's laughing.
He's not paying attention to our class.
That never happens in my class, does it?
No.
I divide that stuff by 4. I get 1.4 times 10 to the negative 12 equals x cubed. Now, how do I get rid of x cubed? Yeah, the cubed root. Okay, so remember we put this fancy symbol out in front. In your calculators, you have this x to the square root. You put 3, that x to the square root. and you put 1.4 times 10 to the negative 12. I would press enter and I get 1.12. Our x is 1.12 times 10 to the negative 4. Very good. And that is our mole slash L again. Questions? Yes.
Why is it square?
That's a really good question. Okay. So the square part, does that make sense because we get it from the coefficient? Okay. So imagine a formula. We're building our formula, or we're building that K. That formula is locked in place by what we've talked about. Now, imagine this, is that for every one of this stuff, we have to get 2 of that stuff. You may think, okay, well, isn't that factored into this squaring? Not really. And so why we have to put 2x is that for every one of the things on the left, we will actually get 2 of these things. So imagine like a currency exchange where, let's say, for example, we went to Mexico and we traded $1 for a peso. And let's say every $1 is worth 2 pesos, for example. That's where that factor comes into play. So it's because this is making it twice the change. Does that make sense? So this 2 down here factors in the change. This square is locking in that formula. Does that make sense? It's something we'll get used to as well. But that's a good question here, and we kind of see it on our final example. Any other questions? Anybody still need it? Okay, moving on here. I'm going to go a little bit quicker here to get to this. What's the point of this? Okay, again, here's where I'm going to use the example, and I've used it before in class. You have iced tea, and you add sugar to it. Can you keep adding sugar to that iced tea, or at some point that sugar will just fall to the bottom? Fall to the bottom. This is saying, hey, does the stuff dissolve, or does our solid go straight to the bottom? Okay, that's why we factor this stuff in here. Now, the examples here, and you can read through these notes on your own. It is saying, hey, what happens in this scenario? And this is kind of a complicated reaction, so I'm going to just skip over it. Like I said, in notes detail it here. Here's the important part. Now we factor in this Q. You think, oh, great, another variable. All Q is saying is, have we reached that maximum amount that we've dissolved in? If Q is less than that K value, then we can add more stuff. Just like the tea, we could add more sugar and keep dissolving it. But if it's greater, we can't. Questions? All right, let's do an example. Now, this problem here, I'm really going to walk you through it because I wish I was a little bit more straightforward. First things first is this. We are mixing NaCl and we are mixing lead to nitrate. Great. This stuff mixes together, and in the process, this is a regular reaction, it forms lead 2 chloride, which is a solid, and it forms sodium nitrate, which is AQ. Again, great. Now, the one thing that I'm not showing you in this process is the balancing, because I'm not really concerned about the balancing process. What I want to do is figure out, in our equation, it says that lead 2 chloride is forming a solid. I want to verify that a solid actually forms. So here's what we do. I'm going to grab that PbCl2 and I'm going to put it down here. I'm going to say PbCl2, which is a solid. We see our familiar equilibrium and we break it down into this. Pb2 plus and 2 Cl minus, and we get this. Now, we factor in or we write down our KSP. So KSP would be equal to PB 2 plus times Cl minus raised to that second power. Very good. Here's the part where I wish I would have just been a lot more straightforward with you, is this. If I mix 100 milliliters of this stuff, NaCl, and 100 milliliters of lead 2 nitrates, what's my total volume? 200. Because we have double the volume, these concentrations cut in half. So here's what I want you to write down. I want you to write down this. Instead of 0.01 molar, because we now have 200 milliliters, technically this is 0.005 molar. And instead of 0.02 molar, technically this is 0.01. Again, all because we have double the volume. And again, I would guide you through that a little bit more and make that a little bit more explicit. Okay, now here's what I want you to think. We have 0.01 molar PbNO3. So in purple, PbNO3, what could we connect that concentration to? The Pb or the Cl minus? The Pb, right? Pb is going to be connected right here. So in place of this Pb, we can actually put 0.01 as our number. Okay? Now, very good. The 0.005 is connected to our Cl. So we can plug that right in. Now, one mistake I made is that we don't know if the solid's formed, so technically this should be a cube. So, here we go on this.
Why are you using Q?
Very good question. We don't know if the solid is formed. We just mixed the stuff together and went, oh, hope it works. We don't know.
I was asking why it was a Q.
Oh, I think, don't quote me on this, but Q question does a solid form. At least that's what I think. There's probably more of a reason behind it. But I like Q question. Good question. I'm sure there's some other science name behind it. But
Right now, it's a question.
yeah, so I'm going to plug these numbers in, and I'm going to say, in my calculator, my Q is this, 2.5 times 10 to the negative 7. Now, I need somebody to help me out here. And for PbCl2, what is the value for that KSP?
It is 1.7 times 10 to the negative 5.
Okay, 1.7 times 10 to the negative 5. Now, we need to decide what is bigger and smaller. This Q has 6 zeros in front of it before the decimal. This K only has 4 zeros.
Okay, that can't be.
Okay, very good. K is bigger than Q, or how we would write it is that QSP is smaller than KSP. Cool. What's that really mean? What that means is that no precipitate forms.
So the answer would be no then?
The answer would be yeah, no precipitate forms. Meaning we would have to add more and more of our stuff to get a solid to form. That's that big factor that we play in here. Questions? One more example, and then we'll be good to go. Does anybody still need this? Just one example. One example.
Now it's done, survey.
Almost there.
Do we have a lab this week?
probably will get moved to Monday. It's gonna be kind of a group lab.
Like, yeah, you're like the whole time.
Yeah, so essentially, you know, that Le Chat liaison, we say shift left, shift right, we'll kind of do that almost as like stations.
So if we don't get that done on Monday, then are we still taking our test on Tuesday?
We'll see, yeah, I'm up for suggestions. Anybody still need it?
I think we should just be done for right now.
Yeah, can our final just be like a regular test, like?
No, it will be part lab final, part,
How are we supposed to find the thing?
What do you mean
Like,
by
will we
find
have
it?
like a set of what it could be?
it's not like, hey, good luck, find this chemical in it. It's lab procedure.
I don't know what that means.
So like, can you follow directions?
So it's
That's-
not like-
It's not like, you know, make sure you go find an example of an atom and pull out an electron.
So will we do that on the day of the final, or will we do that?
We'll do that.
You're gonna give us like an example of how to do it?
Yeah. So this will be our, no, we'll have one more real lab, and then the next lab will be like practice,
And
and
then we
it'll
have,
be for real.
oh yeah, we have like
We have like 6 weeks.
6 weeks next, starting next week.
All right, last thing, and then we'll be done. Common ion effect. Hey, if you add an ion, it affects all those calculations. Cool, great. Oh, look, we get an example. So we have this stuff, which PbCrO4 breaks down to lead and chromate. And so if I said, hey, write the KSP, we would get this. KSP equals lead, 2 plus, there's only a coefficient of 1, so we raise it to the first power, times CrO4, 2 minus, again, coefficient of 1, so we make life easy. Now, already before we start this stuff, we have potassium chromate, okay? And we have 0.1 of this stuff. So if we look at potassium chromate, and we look at the items involved in our values here, what does it affect? Does it affect PV or does it affect CrO4?
Thanks, CR.
Very good. It affects, and it already says, hey, at the beginning, we already have some CrO4. We already have 0.1 molar. Now, does it mention anything about lead? No, so we have 0 of that. What we call this is our initial values, I for initial. Now, equilibrium, there's some change to get there, and then we end up with E for equilibrium. Our ice chart, yeah, this is what we call it. Now, Tori asked a really good question. Where did that 2x come from? Well, it really comes from this change. So in this change, both of these things would get plus x and plus x. Now, in our previous example, where we had 2OH minus, if we had a 2 in front, we would have to put plus 2x. So our change is where that 2 came from. Does that make more sense now? Comes from that change. So at equilibrium, we would get x, and we would get 0.1 molar plus x, okay? Now let me ask you this. X, has it been a really small number or a really big number?
Small.
Very, very small number. So I'm going to put this statement. X is so small, and because it's so small, that plus x really isn't going to change this number. So in this case here, we could just say, hey, that's 0.1. So when we go and we factor this back in, and we say, all right, let's find the solubility of this scenario, all we have to do is this. Number 1, what is that KSP of PbCrO4?
2.3 times 10 to the negative 13.
Is equal to, I don't know how much lead, so we say X times our 0.1. And so all we have to do, I'm just going to rewrite this, 2.3 times 10 to the negative 13th equals 0.1 X. How do we get X by itself? Divide by 0.1. This makes life easy. And so when we divide by 0.1, we end up with 2.3 times 10 to the negative 13th divided by 0.1. 2.3 times 10 to the negative 12 moles per liter equals Rx. Okay? Questions? All right, last thing is this. First off, anybody need it? Last thing is this. Last three things. Why this is important. Number one, if we add stuff, which way does the equilibrium shift? Adding it shifts it opposite.
Yeah.
So if we added CrO4 like we did, it shifted left, meaning more solid forms. Down here, I said, hey, add more SO4, again, shift it left. If add it, shifts opposite. Add up, yep. Why this is important? Real world chemistry, right? You hear about lead contaminants in water. We can identify via the process that we talked about what bad stuff or good stuff is in some of our water sources, is in some of our rivers, streams, things like that. And that's that example that we follow there. This right here just helps you identify an example of what you could predict or what you could have in a certain sample. All right. So that was a long day of notes. Any questions? Okay. I will post thy homework. It's not due till Friday.